Hello, this is Ali Khatami with SCS Engineers. Thanks for taking time out of your busy schedule listening to this presentation. The subject of this presentation is final cover geocomposite drainage layer over concaved surfaces. When it comes to closing landfalls, majority of the slopes that we deal with during partial closures are like 3-to-1 slope or near 3-to-1. The flatter areas normally on top of the landfall. And the 3-to-1 slopes are in majority of the times is a straight slope from the top of the landfall to the bottom. In a sense, when you line the slope, which is the barrier layer for the cover system, and you deploy a geocomposite, which is the drainage layer above the geomembrane, water that reaches the geocomposite drains straight down from the top of the slope down to the bottom of the slope within the panel width of the geocomposite. So in majority of the cases there's no flow crossing from one panel to an adjacent panel unless you are on a curved surface, and curved surfaces are in a great majority of the curved surfaces are in convex form, meaning around the corners of the landfall. But if the geometry of the landfall footprint is such that you end up with a concave surface, the geocomposite role becomes a very important matter in the design of the drainage layer for the final cover system. And the drainage layer geocomposite sand may be in the same category as well. On concave surfaces is the subject of this presentation. This is a simple presentation of a concave surface. To the right side of the slide you have a 3-to-1 slope from the top of the landfall, which is the crest line, to the bottom of the slope. On the bottom side also you have a 3-to-1 slope from the crest line down to the toe of the slope. In between them there is a curved surface, which in this geometry is a concave surface. And the two outer dashed lines represent the boundaries of the concave surface, and the middle line represents the center line of the concave surface. The arrows indicate the flow in the composite. As you could envision, if the slope concave surface is covered with panels of geocomposite, there is an intersection between these panels in a very ideal case along the center line of the concave surface, and the flow in the geocomposite can potentially cross from one panel into an adjacent panel and eventually get concentrated and converged toward the bottom of the slope. And there are certain characteristics to a concave surface that I'm going to discuss it on the next slide, followed by many pictures that I'm going to show from a partial closure project, that the geometry of the slope is very similar to this sketch on this slide, meaning it has a right side slope going down up to the bottom at 3-to-1 slope, and another slope at 3-to-1. The one to the right slope, I'm going to be referring to it as a south slope of a leg of a landfall, and the other slope pointing to the south, to the bottom of the slide, is the east slope of another leg of the landfall, and the area in between is the concave surface around the corner of the landfall. Important points with concave surfaces. The top of the slope is much wider than the bottom of the slope. So, and the basin, drainage basin for the geocomposite is a pie-shaped area. In an ideal case that the two sides of the landfill are coming at each other at a 90 degree, the pie shape is like a quarter of a circle. And in other cases that the angle is different, it's like a pie shape. And over the pie shape area, over the concave surface area, flow converges as it approaches the bottom of the slope. So the hydraulic head in the composite increases because of the convergence of water in the geocomposite. If it gets to the point that the hydraulic head in the composite exceeds the thickness of the composite, the water starts coming out of the composite, going into the soil layer above the composite. That causes saturation in the overlying soil, as well as creates pore pressure in the soil layer above the composite, which is a major issue from a stability and design point on the such surfaces. This is a photo from a partial closure on a subtitle D landfill in Florida. The slope that you see in the background in front of you is the south slope of one of the legs or wings of the landfill. And the slope that you see in front of you on the foreground of the slide is the east slope or another portion of the landfill. These two slopes come together at a 90 degree angle, and the area in between them is the concave surface. That is the area that has not been covered with geomembrane yet. This slide, as a matter of fact, shows the geomembrane installation stage of the project. Here it shows the upper part of the concave surface. The soil has been graded properly and it's ready to receive geomembrane, and the geomembrane panels are going to be installed in a certain way that is up to the superintendent of the installation crew. This is what I meant by the geometry of the panels. As parts of the concave surface is already covered with geomembrane, and the only one small area near the top is remained to be covered. So it's the superintendent of the installation crew decides how to deploy the geomembrane panels in order to come together. The installation of geomembrane panels is not as significant for the discussions related to the geocomposite and the issues with the concave surfaces. And the next step, which is the installation of geocomposite, is the important part of it. Here is the after completion of the geomembrane, a picture from the bottom looking up, and on the two sides of this concave surface you can see the beginning of other slopes that run straight up and down on a 3-to-1 slope, and between these two lines is the area of the pie, the concave surface. And as you see, the geomembrane panels are intersecting along a line which you can refer to it as a center line of the concave surface. But because of the special shape of the geometry of this concave surface, for this special partial closure case, the center line ended up to be not a straight line all the way to the top. There is a kink to it that you will see that later in another slide. This is where the geocomposite installation comes about. The slope in the back is already covered with composite, straight runs from the top of the slope to the bottom, and at the very bottom geocomposite has reached the corner, the very bottom of the concave surface. And in the foreground, geocomposite also is installed on a straight up and down kind of runs of the landfill slope, and again in between is the concave surface. Now, in this slide, the installer has already started installing geocomposite in the concave surface, And again, it's up to the installer how to deploy the composite panels. And if a designer has a tendency to define the geometry and the runs of the composite, of course, more than welcome to do that in the construction drawings. But if it is not defined, the superintendent of the installation crew will decide which way the composite goes. This is a completed stage of the composite installation. As you can see, the panels are running into each other. In the very back of the concave surface, there is panels are running from north to south, from the top of the slope toward the bottom. And in another section in front of it, closer to us, the panels run from west to east, west being the top of the slope, east being the bottom of the slope, and they are all intersecting. And as a result of this, we have a lot of cross-panel flow in the composite. If you want to define the flow path of water in the composite. This is a kind of another view of the same. The lower portion of the concave surface is not covered with composite yet, but again you can see the directions, different directions of composite running on the surface. Another view of the same slope. The lower part of the concave surface is not covered with composite yet. Here is getting very close to the final stages of geocomposite deployment. You can clearly see in how many different ways these composite panels are running and covering the slope. And there's again, it's up to the installer superintendent how to run these panels and make them fit together. This is after the completion of the geocomposite. We had a big storm. The storm managed to wash down some of the dirt from the top slope, and the dirt happened to kind of leave a stain on the geocomposite. The stain clearly shows the flow pattern of water in the concave surface area, in the pie area, and you can see that there's a lot of cross-panel flow in the pie-shaped area. And when it comes to the bottom of the slope within the pie area, there's a concentrated flow reaching to the bottom, which is that convergence of the water in the geocomposite. This is the completed funnel cover, and the concave shape, I think it is visible. The terraces are tack-on swells that are constructed above the geocomposite wall, installing the upper kind of soil layer. This is another view of the completed surface. To the left side, you can see the concave surface, and the center line of the concave surface almost falls on the very left side of this slide. The story was that probably a month or a month and a half after completion of the cover system, we had a big storm, and within a few days we were informed that we needed to do a site visit. When we went out there, we noticed that water was coming out of the soil layer at the surface of the grass near the bottom of the slope and flowing down over the surface of the slope. So we started thinking what could have caused this, and we arrived at the concave surface phenomenon and impact of it on the drainage layer in the composite. So because of the convergence of water in the composite, the hydraulic head in the composite exceeded the thickness of the composite. Water entered the soil layer, and near the bottom it was so much water in the soil layer that it started flowing out of the soil layer, running down the slope on top of the soil layer. So we started thinking how we can address this issue and how we can solve it. And we came up with this solution. I'm not saying that this is the only solution with these cases, but we arrived at this solution because the partial closure was already constructed. And the solution was that we kind of devised a drain system directly on top of the composite along the center line of the concave surface. And this drainage system, it was a very simple system. It was a perforated pipe embedded in gravel and a geotextile wrapped around it. And we connected this drain system at the bottom of the slope to a rainwater tow drain system at the bottom of the slope to capture the water from the perforated pipe and release it into the perimeter ditches. For the construction of the drain system, we started with fabricating perforated pipes. In this slide, it shows that the crew is welding pipe segments together to have a long segment for pulling into the trench. Then a trench was excavated along the center line of the concaved surface. Like I stated earlier, the center line ended up to have a kink in it. I'll show you on the next slide the alignment of the trench. In this slide, you see that the trench is excavated all the way down to the top of the composite, and the drain system sits directly on top of the composite. If water gets in the composite, the composite becomes saturated and water comes out of the composite, it will get into the perforated pipe and flow very rapidly to the bottom. That would prevent saturation of the soil above the composite. Here you see the alignment. The lower part of the slope, the trench is already backfilled. You see the surface of the dirt backfill in the trench, but somewhere up there, when there's a roll of the geotextile is placed across the width of the trench changes angle because of the center line of the concave surface. The geotextile goes in, directly sits on top of the composite, and the perforated pipe gets installed inside the trench. You don't need really gravel below the pipe to protect the pipe because the surcharge loading is very small. So we put the pipe in the trench directly above the geotextile, and then the gravel goes in the trench. Here is the stage that the gravel is being placed in the trench. Then the gravel gets graded and shaped around the pipe and a smooth surface. And then after that, they pull the geotextile together and close the burrito. Following completion of the burrito, they come back and backfill the trench and shape this slope to what it was before. And the impacted area, disturbed area, gets sodded. Again, we are not saying that this is the only way to address the issue, but we are recommending that the designer would evaluate the concave surfaces and devise measures in the final cover system ahead of time before the construction to address the convergence of water in the composite. Conclusions: concave surfaces require special attention at the design stage. The convergence of flow in the composite is of extreme importance. Evaluation needs to be performed in order to estimate volume of water flowing down to the bottom of the slope, and from there devise measures to handle excess water in the composite in the lower portion of the slope. And also special discharge point needs to be designed at the bottom of the slope to take away water from the perforated pipe and discharge it to the perimeter ditches. That needs to be kind of designed at the design stage of the project. With that, I conclude my presentation. Thank you again for taking time out of your busy schedule listening to this presentation. If you needed any clarification or if you had any questions, please don't hesitate to contact me via my email or on my cell at 561-441-1473. Thanks again.